Alright, we've talked about the var and the sort description operator colon equal to, but there is another built-in way to create a variable in Go that is specifically useful when you need a pointer to a new function. Let's break down what it does. The new function is a built-in function, so you don't need to import any package to use it. Its main job is to do three things. First, it creates a variable of the type you specify. Second, it initializes that variable to a zero value, as we learned. For an int, that's zero. For a string, that's an empty string, and for a boolean, it's false. And finally, it returns the memory address of that newly created variable. In other words, it gives you a pointer. The general syntax is p colon equal to new t, where t is the type you want to create. The variable p will then be the pointer to the type strict t. Let's see the practical. Here in our main function, we have p colon equal to new int. The line tells Go to allocate memory for an integer. Initialize it to zero value, which is over there, and then assign the memory address to integer, and the p will become strict int, which is a pointer to an int. And in next line, if we print that thing, we would get go run 0, because it is 0 over here. And if we want it to change, like in the next slice, it shows that how can I change that variable value, and we can do it using strict p equal to the symbol or the number whatever I want it to get changed. And then if I'll print it, I would get 2 in the second line, which I have changed with this. Next slide is, so you might be thinking the new function is a neat, but couldn't I just do the same thing with a variable and taking its address? So so to answer that, this is really important point to understand. The new function isn't some special low level memory operation. It's what we call syntactic convenience or syntactic sugar. It's just cleaner, shorter way to do something you could already do. Let's look at these two code snippets. They might look different, but their behavior is identical. On the top, we have a function newInt that returns a pointer to an integer. Inside, it says return newInt. As we just learned, this allocates a zero size integer and returns a pointer to it. Now look the second version of it. NewInt dummy, we create a dummy variable int, then we return pointer to that int. This function does exactly the same thing, just more explicit way. First, it declares a local variable called dummy of type int using dummy var dummy int. Because we don't give it the initial value, Go will give it to a zero value, which is here actually a 0. Then it returns the memory address of dummy using the address of operator. Ampersand is called address of operator. So both of these function creates a new integer variable initialize it to 0, and then returns a pointer to it. The end result is exactly the same. The key takeaway here is that new is just more concise way to express these patterns. It gives you from having to come up with a dummy variable name just to take its address. It's convenience, not a fundamental different memory model. Take a look at this example. It's very simple, but it demonstrates the point perfectly. In the first line, p colon equal to new int, we're asking Go to create a new integer variable that give us a pointer to it, which we store p. The second is q. We do exactly the same thing. Go creates another new integer variable and gives us the pointer to it, which we store in q. Even though both strict p and strict q would have the same value 0, the variable p and q themselves holds the memory addresses differently, as because new create a fresh variable each time, the memory address will be different. So when we get to the third line, and which is fmt.println p equal to q, we are asking a specific question. Do the pointer p and q points to exact same memory address? And the answer will be no. They points to two separate distinct integer variable. Therefore, this line will always print false. The main takeaway is that the pointers returned by calls to new will never be equal. There is a small technical exception for what you called zero size type, but for that we'll get to a next slide. In the last section, I mentioned a small exception to a distinct memory address rule for something called zero size type. This is a bit of an advanced topic, but it's interesting and help complete the picture. So what is zero size type? As the name implies, it's type that takes up 0 bytes of memory. Let's look at the most common example. The empty struct. An empty struct written as struct is a struct with no fields inside. Since it has no fields to store it, it requires no memory. In this code, we declare a variable s of type struct. Then we use a special function from unsafe package sizeof to check how many bytes s takes up in memory. As you can see, the output is 0. So with the array of zero size type. Now, what if you have an array of these empty structs? Here, we are creating an array named ARR with 1000 empty structs. Well, if one of them take 0 spaces, then thousands of them also take up 0 spaces, as 1000 times 0 is still 0. All is 0, and the size also would be 0. So with this struct containing only 0 size type, this logic extend even further. Here we've defined a metadata struct. Notice its field. The first is an empty struct and the second is an array of 10 empty structs. Since all of its internal components are 0 size types, the metadata struct itself is also a 0 size type as expected. And by checking the unsafe dot size of m metadata, the output would be 0. This is a niche corner of the language, but it's good to be aware of. You might see empty structs using as placeholder in maps or for sending signals on channels without needing to send actual data.